Hello, I'm Max Mortillaro from TECHunplugged, and I'm reporting on Intel Memory Summit, the virtual event for 2020, also called the Intel Memory and Storage Moment. So we had a great moment talking with Intel or hearing them, and some of the announcements from this event were around Intel's split, or rather sale of their 3D NAND division to SK Hynix. They were presenting some of their products, which we have covered in our blog at techunplugged.io/blog. And they were talking primarily about announcements about 3D NAND SSD drives, which we're not going to cover in this video. Announcement of the second generation Optane memory, rather 3D NAND version 2 somehow. And they were announcing the Optane PMAM 200 series modules. So these are DIMM modules of Optane persistent memory, so they're used in a DIMM slot, and they're close to the processor, and also the announcement of a new Optane SSD. So we're not going to talk about the SSD today, and all of the product announcements are on our website, so please head over to them if you want to get some detailed specs and all. What I want to talk a bit more about is about Optane and what does it mean for the future, so let's get around that. So as you know, Optane is a very different kind of media compared to 3D NAND. 3D NAND is made of several cells of memory, where each cell has a certain amount of bits based on the density, single layer cell, multi-layer cell, triple layer cell, QLC, which is quadruple layer cell, and we even got a glimpse of what's next with penta-layer cell, so it means 5 bits per cell. No, the thing with 3D NAND is that, first of all, you have big stacks. It's like a skyscraper of cells, and each vendor, of course, has their own technology. Some have their floating point, floating gates. I think it's Intel. Others have charge trap flash. Anyways, everybody says that theirs is best. The thing with that is that the amount of cells, the amount of bits you put in a cell is based by varying the tension on the cell, right? So you have more states, but the more states you have, the more let's say fragile your media starts to be, especially because in an SSD, in a 3D NAND SSD, you're not writing each cell somewhere individually. You have a page which is made of multiple cells. And as this little cat in front of me is saying, and agrees probably, you need to write pages and arrange pages, which means that even if you need to write something in a single cell, then what you need to do is that you need to write your information. If you need to erase it, then you need to erase multiple cells, even if you just wanted to touch one single bit on one single cell. So that's a durability problem that increases with the density that you are putting in a drive. If you have single layer cell, then it's simple. You're just changing one bit in one cell. But the more you have, the more it has an impact on the media durability. When you're dealing with Optane, which is a totally different kind of media, Optane is a kind of let's say kind of matrix, kind of a 3D kind of matrix. It's really hard to represent. Actually, I had a 3D printed one from my friend Stephen Foskett from TechField Day, but I don't have that to show to you now. But anyways, the big difference there is that it is a byte addressable media, which means that you address each byte individually, and you can write each byte without impacting all of the other bytes which are on the media. And that makes it much more durable. And not only is it durable, but it is even faster. It is much more, I would say faster, because it has a lower latency and so on. And that makes it really suitable for the most demanding workloads. And what that means is that you can put it very close to the memory, very close to the processor, and use that either as a kind of let's say extension for your memory. Actually, what you can do is put it in front of your memory, use some DRAM, which you use as a cache, and you put your Optane here, and the Optane shows up like if it was memory. So actually the same as you will see in some, hard drive architectures, where you have a cache and the actual storage capacity tier, but I think that's for kind of a memory architecture. So if you want to have, for example, to show 1 terabyte of data, on 1 terabyte of memory on your server, you would front 1 terabyte of Optane PMEM with, I don't know, 384 maybe megs of RAM, or maybe 512 of RAM. And that's going to operate as a memory with more or less the same speed. I mean, the advantage is that you get more capacity at a cheaper price, because of course Optane PMEM is not really cheap, but it is still cheaper on a, let's say, per gigabyte basis. It is cheaper than DRAM, and therefore it allows you to increase the density while lowering the cost or maintaining the cost similar. So that's one of the use cases. But the other use case, which is even more important, is how that impacts storage architectures, because you get to storage architectures which are going to leverage more and more Optane and flash memory, especially capacity-based memory like QLC, because it is high capacity, because it is relatively cheap. And the main issue that QLC has is durability. It is not very endurant, and you need to be especially aware of how you write your data to QLC drives to ensure they do not wear out too fast. And that's where a good architected storage system comes into play with Optane, because if you write your data to Optane drives and have enough capacity on the Optane drives to retain the information there persistently, and then be able to kind of shower or let it trickle down to the capacity tier, to QLC, by writing large enough blocks in a way that you're going to use all of your QLC drives efficiently so that they wear out at more or less the same level, then you would be in a relatively good position. And we've seen our friends at Vast Data do that very efficiently. They've been presenting at several field day events. They've been quoted several times by the execs at Intel during the presentations. If you don't know them, I really encourage to check them out, especially our friend Howard Marks, who can tell you a lot about them. And that seems to be, at least in my opinion, the future of where the storage industry is headed at, in terms of finding a great, let's say, compromise between capacity, performance, and price. I mean, and when we talk about even performance, by the way, we're by the way talking about, reducing one in favor of the other. I mean, Optane drives are just so great, and the technology is so great. It's using, by the way, NVMe, so it's connected via PCI Express, so it has a very, very fast throughput. So provided that you have the right components in there in the drive, so same processor level, supporting the latest NVMe Optane, or actually if it's not even NVMe, if you're using Optane PMEM, I'm not sure which one Vast is using right now. If you're using all of that together and the storage architecture, the storage layer is properly architected, then you probably will not find a performance problem or performance bottleneck. So that's, in my view, where the industry is headed at with flash primarily. Yeah? So that said, what does the penta-layer cell, so 5 layers, 5 bits per cell, what does it mean for those architectures? Well, in fact, it doesn't mean a big change at all, because what's going to happen there is that those drives will have different endurance characteristics, and primarily also because those drives are new, so it will take some time perhaps to fine-tune the 5-layer cell technology before we get to relatively good endurance levels. But in terms of storage architectures, what changes is that they will just have to change the, let's say, the amount of the size of write stripes, the size of blocks that they're writing to, and that's going to be the only fine-tuning, because otherwise, in terms of bandwidth, probably in terms of latency and so on, it might remain pretty much the same. So that's all for this video, which was more or less covering storage architectures. And I'll be soon back with another video which is going to cover Optane more in the context of direct memory use cases, persistent memory, and so on. Thank you and stay tuned.